Hi everyone. I hope you're enjoying the conference so far. My name is Pedro Albuquerque, and I work at the Database Reliability Engineering team at Miro. And in this talk, I will share how we enabled automated deployments for PostgreSQL RDS using Terraform and GitLab pipelines, how that led to an increased delivery speed and applying best practices configuration and make them consistent. But first, for those who don't know me, I'm from Portugal. I'm based in London. I moved to the UK many years ago. And I've been working with databases, mainly open source, for the past 12 years. Outside work, I play handball. I've been playing that for over 30 years, but I think it's time to retire. My knees already complain about that. And I also have interest in reportage film photography. Let me go quickly through the agenda for today. I'll share a bit about Miro. I don't know if every one of you knows about Miro. I'm going to share about a little bit about its hypergrowth and the challenges that came with it. I'll also go through the new deployment strategy implementation because of those challenges. We had to address them. I'm going to share the main takeaways and what's next for Miro in terms of Postgres infrastructure. Let me introduce you to Miro. It's a digital collaboration platform. It's helping on-site, hybrid, and remote teams to create the next big thing. One of our major products is a whiteboard tool, and in that product, you can in real time collaborate with hundreds of other people. It was established in 2011 as real-time board, rebranded later as Miro. At the moment, we have over 1,800 Mironeers working globally across 12 offices, and many of us are actually remote. And we do support and we develop features and more products to our users worldwide. At the moment, we have over 50 million users using a platform. This is a little snippet of who are our organizations, who use Miro, actually. This is a really nice number. 99% of the Fortune 100 use Miro. And as far as I know, Percona also uses Miro, so it's a good thing. So I'm going to check here what drove our hypergrowth. 3 years ago, a pandemic shaped our world and reality. A worldwide lockdown sent people home. Offices were closed. So we entered a new normal, and that new normal was online collaboration, distributed teams. And Miro was at the right time, at the right place, because it really answered the need to facilitate this online collaboration. And that was the thing that triggered our hypergrowth. From the beginning of the new normal, let's say, until today, our use base increased 10 times. Our use base increased 10 times from 4 million to over 50 million. Miro grew as well. We grew 7 times in terms of number of Mironeers. The data generated by our customers grew around 30%. And looking at the number of Postgres database clusters, self-managed database clusters for our monolith, grew from a few in the beginning of 2020 to over 200 at the end of the first quarter this year. So that's a lot. We increased a lot. With the hypergrowth, obviously, new challenges come. Our monolith became a huge bottleneck for our engineers, for our engineering teams. They had to work on the same code base, therefore code became more complex. The teams did not have the autonomy they wanted. They wanted to deliver faster, and which affected our time to market. So to address some of the challenges that came with the hypergrowth, engineering adopted microservices architecture. Obviously, it's not what I'm going to share here is what we did to enable the teams to drive faster. Obviously, there are other challenges that obviously come with microservices. But I'm going to focus on the databases infrastructure, not on the challenges that event-driven architecture come, implementation Kafka, etc. that pops up. So I'm going to focus only on the data stores. So with hypergrowth, there are challenges. So with the adoption of microservices, there are challenges that will rise. The PostgreSQL RDS was chosen as the relation databases for microservices who wanted to use relational databases. And the reason is there was already expertise within the engineering team since we're using Postgres self-managed for our monolith. RDS or RDS? On the self-managed, we use RDS vanilla Postgres, not Aurora. Yeah. So the challenge is when microservices started to grow, and obviously with this growth of infrastructure during our hypergrowth, infrastructure team was still very small. It's hard to hire. It's hard to cope with the growth. There were simply not enough resources on the engineering team that were dealing with platform to cope with this growth. But the infrastructure team at the time, they were doing their best on creating ad hoc RDS as the requests come. So at the time, we didn't want for us to be the blocker to avoid the teams and block the teams to develop and deliver. But unfortunately, many of those RDS did not follow best practices, which led to misconfigured deployments. Let me share with you some examples of what a misconfigured RDS was. So, no naming convention whatsoever. And this applies to the RDS resources, either the RDS itself, RDS proxy, but also the internal things like the logical database, the schema, and actually the database users. So there was no naming convention, which if we want to apply some kind of automation, or it's really hard, even to if we are paged and we need to go and look for the database, there is no information about this service and actually the environment. So it was really hard. Many of the RDSs that were delivered had just one single database user, which actually was the RDS main user. So the service was running with the Postgres user. The flyway was running with Postgres user. Read-only workload. I mean, every single application. I mean, the application that may had different different roles. I mean, different types of workload. They were using the same Postgres user. Secrets for this user, they were generated locally and pushed to database secrets manager, which is also not great. We had even new RDS clusters that were being created with old Postgres versions. We had from 9.6 to 13, like 9.6, 10, 11, 12, 13. So it was really hard to maintain all of RDS. So this is RDS. On-prem, we were using, actually we're keeping everything on 11 and planned, and we made plans to upgrade it. But for microservices, it was kind of a zoo of versions. Almost no observability. Apart from a few ones, the majority did not have the PG statements enabled. The performance insights, although it's free for 7 days of retention, they were not enabled, and Prometheus Exporter was actually were not deployed for the majority of RDS clusters. And other misconfigs, multi-AZ not enforced in some deployments, for production deployments and different backup policies. So we were in not great shape, I'll have to say. When it comes to infrastructure as a code, it was also not in a great shape. The copy-paste from existing deployments was the norm. So there was not a template, which means if the copy-paste was copied from a deployment which were already with some bad configurations, there was propagation of these mistakes, right? Many RDSs were created without production-grade setup. Also, the way the resources were defined in terms of layout on the IAC repository. Let's say we want an RDS with a proxy. These resources were treated independently. So we had to create first the RDS, then pick up the output, and then put this output as inputs for the proxy. So it was a lot of operational burden on this. Also, the naming convention did not take into consideration the blue-green deployment. So it was hard to follow. Leadership then realized that there was the need to have database specialists, a team that knows better how to run databases in production, to make them highly available and to run them actually at scale as well. That would also relieve the other platform engineers who were dealing with other parts of infrastructure, security, networking, Kubernetes. So they gave the database team all the responsibilities and ownership of data stores. So the database reliability engineering team, it's pretty new. It has 8 months, say. It's focused on better data source operationability. We also are helping on extending the infrastructure as a code and giving our inputs to the rest of platform. How to make the IAC actually support data stores deployment and specifics, because data stores are completely different from, the way you manage them are completely different from application servers, for example. Other type of resources which are stateless. We also define the production ready setups and non-production ready setups for cost efficiency. We are also responsible to consider adoption of other of other data stores for workloads which where it fits better somewhere else. Obviously, here we have to work together with the product teams and the architecture team. But it's something that we also have to own this. It's part of our responsibility. And another one is the database as a service vision. So we are already working on that, and RDS PostgreSQL was the first one. Still, we need to evolve a little bit, but the idea is to have database as a service to our product engineers. So we kind of abstract the infrastructure. Not that they have to know how, like what is a Postgres RDS, how it works in terms of multi-EZ, etc., which will impact write throughput, etc. But it's more an abstraction on the terraform and how to create them. That's the main goal of this. As part of delivering that database as a service, we define the RDS deployment requirements. These are just some of our deployment requirements. So we want fully automated deployment with a minimum of human intervention. And the reason is we want to offload these deployments to service teams, right? There's no point of us being the bottleneck of this. We want all the deployments to be standardized and repeatable, because for our DR, right, we want our DR to have a similar setup. In the deployment, we don't want to generate secrets and push these secrets manually, right? So we want this deployment to do that. We want to limit the amount of Postgres versions, and part of these deployment requirements we look at as well at those deployment being cost effective. And for that, we revisited the deployment we had at the time, and we decided, okay, we had to adopt a new deployment strategy. We started from the ground up, as in we started from the Terraform modules layout. We had to restructure them. We adopted the layout where we have, within a single version repository, 3 layers of Terraform modules. This makes the relationship and creating the relationship between resources very easy. There are 3 global modules: RDS, RDS proxy, and Prometheus exporter. These ones create the infrastructure, right? They are responsible to call the AWS provider. Then these are encapsulated within what's called a business logic module. And this business logic module is the module which is responsible to aggregate all the deployment requirements, enforcing multi-EZ in production environments, this kind of stuff. So we apply our business logic there. And then a live module, we call it a live module, which will encapsulate the business logic module. This module the live module will receive a YAML configuration file with the RDS configuration as input. That's the only thing it does, because if we have different or multiple RDSs to create, it will iterate through the YAML file. Let's go into a bit of details of which module does. One thing, we decided to keep all these modules within the same repository because we don't have the need. So this RDS proxy, and permitted export, they are not called anywhere else. So they only make sense to live together. But we could split this and create the versions repository for RDS, another one for the proxy, another one for the permitted export, and then the business logic module would call this. But since it's only used here, there's no point. And we structured it this way since it's easier to understand what goes first, what goes second, and what goes last. So for the global modules, the RDS basically creates the resources which are needed by the RDS. Database cluster, parameter group, IAM roles, security subnet groups, the CloudWatch alert logs, and SNS topics for notification. So teams can actually subscribe these topics and have them sent to PagerDuty and VictorOps and other notifications. For the proxy, the same. It creates proxy resource, the proxy target group, authentication scheme, CloudWatch alerts, and IAM roles. For the Prometheus exporter, this one creates the Prometheus exporter in our Kubernetes cluster. So a cloud team gave us a Kubernetes cluster where we actually can create via Terraform. We create the containers and pods there. So this will automatically do that. Obviously, we have to pass the secrets for the user, for the observability of the user, etc. But it does everything. We don't have to, after the RDS is created, we don't have to go and create the exporter. So it does everything. We will be looking at that later. It's something that we don't use it yet, but for the service user, we plan to use IAM authentication. But it's something that we are testing actually. The business logic module, which encapsulates those three modules I spoke about, sets best practices for each type of environment, apply the naming convention. It creates the secrets for database users and proxies, so that there's secrets for the proxy and secrets for the database. It does not generate the secrets, it just creates the secrets resources. It also supports the blue-green deployment. We'll go over that in a bit. And one important thing is it calls a Lambda, the AWS Lambda invocation resource, which is this Lambda that will generate the database, the different database users, pushes these credentials into the secrets that we created, the secrets resources that we created. And also, it creates the users in the databases with best practice privileges, and then sends the notification. But we will go through that in a bit. And then live module. It supports a YAML configuration file as input, and it creates, since it encapsulates everything, it creates one or multiple RDS clusters. RDS clusters can be comprised of an RDS, an exporter, and maybe a proxy or not. This depends on the needs of the workload. So this is an example of what's needed to set to configure. This will configure an RDS cluster with specific instance type, in this case R6G large. We define the storage, size, type, IOPS, and then a map of parameters. These parameters can be override. They will override the parameters we set as production ready, as in the business logic module. So in the business logic module, we have what we think are the production ready parameters for the default, which are the parameters that are used in the versions we support, and we have specific ones for 14, specific ones for 15, but these ones will take precedence on those. In case we have we have an RDS that we need to tweak a little bit more. And also, with the proxy enabled, we can enable a proxy or not. That depends on the workload. I want you to notice the details on V1 and V2. This is how we approach blue-green deployments for situations when we need to apply rolling maintenances. Also, I'll go a little bit into details on that later. But as a start, we set up the blue deployment as V1, and then V2 false. So we don't pay money, right? I mean, we don't pay extra money. When we want to switch over into a major version using rolling fashion, then we set enable true. And with the configurations that, for example, the version is going to be 15, so it's going to spin up a cluster with version 15. We also had to restructure our terraform layout. So I spoke about the restructure of the terraform modules, but for the infrastructure as a code where we actually define all the resources, we actually have to restructure a bit. In the past, it was more environment and service oriented, environment and resource oriented. And we set the repository service oriented. We also are using TerraGrunt. I don't know if you know TerraGrunt. It's a Terraform wrapper. So we don't need to repeat, for example, service and the environment configs for each one of the resources we create. We define it once, and then they are passed as input to the resources we create. So this is a layout example for service A and B. On the root of the repository, we have is where we define environments. This is an example for a staging and production environment. In the environment HCL file, this is where we define the specifics for that environment. We define VPCs, we define the security groups we want to allow connections from on the RDS, for example. So all the environment-specific configurations that will have to be used by the majority of resources, they will be there, and the same for production. Also, on the root of the repository, we define services. And within each service, we define the environments where they're going to be deployed. Then within each environment, we define what are the resources that we are going to be deploying. For service A in this case, let's look at staging. In staging, we're going to deploy an RDS and Dynamo. In the RDS, we just need that configuration file I showed you and the TerraGrunt. The TerraGrunt file is the file that's going to have the config as input, and it's going to call the live module. That's what it does. It doesn't do anything else. And obviously, it imports. There's a configuration there that is going to import the other YAML files defined, or the HCL files that are defined on the environments. And then for service B, we have a similar structure. Do you remember the reference I made to that Lambda on the business logic module? This is actually one key part of our deployment because that removes a lot of operational burden and keeps consistency of database users and privileges. The main features of this function, it generates database users credentials, sets the credentials in the AWS secrets we pass, It then creates database users with safe privileges. So it creates a user for Flyway, creates a user for the service read and write, creates a user for read-only workloads, creates a user for the observability user, and so on. Another very important thing about this function, it's idempotent. So we wrote it in Python that if we run multiple times, the output is going to be the same. So if the users already exist, it doesn't do anything, right? It's something that we wanted to make sure that if by any chance this function is ran again, we don't impact production or the instance. Yeah. It also notifies the service team when it's ready. So when the users are ready for them, it shares with the service team in Slack. It's sharing the endpoint, shares the endpoint. If it's using a proxy, it shares a proxy endpoint. If it's not using a proxy, it shares the CNAME endpoint. That's going to point to the RDS. So whenever we do switchovers, even if we don't have a proxy, service configuration is going to be the same, right? The failover is going to take a little bit more time because it's not using a proxy. And for integration tests, we use the local stack. So this is a pretty big slide, as in is not gonna, the details are pretty small, but I'm gonna actually show Miro. So this is a high level of the AWS Lambda function workflow that we wrote. So at the end of the creation of, you can define dependencies on Terraform. So at the end of creation of a proxy, what we do, we call this Lambda function. So we call this AWS Lambda invocation resource. If we are creating a read replica, obviously it will not call, right? So we keep it. If RDS is a primary, which means it's like a regular cluster, this is the JSON that we pass to the AWS Lambda invocation resource. So we pass the RDS endpoint, we pass the database name. This is the service database name, which we create on the RDS global module. We pass the password that was created by AWS when it's creating the RDS. It always creates a random password because Lambda needs to connect. We pass the secret name, which is a secret that is going to contain all the user's credentials. We also pass Postgres extensions. Some services may require more extensions. So it's going to iterate through the extensions and it's going to install them on the service database. Then we pass details of proxy. We pass the proxy endpoint. And then we pass the two secret names on the AWS secret, because the way it works between proxy and RDS is proxy needs to have a secret with a JSON username and proxy, which needs to be, this user needs to be defined on the database. So the proxy does not understand a big JSON of where we have our specific, service arrow username, service arrow password. So it just understands username and password. That's why we have to create different secrets for a proxy. But basically, they will have the content username, the read, write, and the password for it. And then the other secret is going to contain the username and password for the Flyway. And then we have the CNAME endpoint for the services which not use the proxy. Then what it does is it will check in the secrets manager in the secrets if the secrets are already there. So it checks the layout. I mean, it checks what the content of those secrets. If the secrets are there, it's going to check actually if the users have been created. So it's going to check every single user, see if the passwords match, if we have an error logging in. If it does, then the database has been set up correctly. It's one of the checks we have. We have other checks, but they are not here. Yeah. If the secrets are not in the secrets manager, then this function will first generate secrets. Then it's going to run a batch against the Postgres database. This batch is going to create database users and passwords. Then it's going to run the service batch, which is it's going to create extensions against the service database. It does other stuff. And one very important thing is this reset Postgres password. I mentioned we pass to this Lambda the password that was generated by the AWS RDS. The problem is that password is in the state file, and for us is kind of security breach. Although we have measures for people not to have access to the state files, but still, it's something that we don't want. So what it does, it resets the password. So the password that is in the state file becomes invalid, and the Postgres password is in that secret. So the Postgres password was also generated here. So this step generates secrets. It generates secrets for the Postgres user, read-only, fly-away, read-write, and observability user. And then at the end, if everything goes well, it sends a notification to the service team, and then it ends. Any question here? Do you? Yes, we have to. Okay. Yeah, I mean, it's something that we have to have idempotent. We cannot risk having instances in production being affected, because this Lambda invocation resource, the moment you change this JSON, even if you add, I mean, by any chance, I don't know, by mistake, the password, this local password changes, or someone edits on state file, it's going to run again. So this Lambda invocation runs every time you change any of this JSON. So we wanted to make sure that's idempotent. Let's back to the slides. So let's talk a little bit about blue-green deployments. A blue-green deployment is a deployment strategy in which you can create two separate but identical clusters. One cluster, blue, is actually running the production workload. The application is pointing there. And then the other one, green, is running the cluster with the changes that you want to apply. I mean, to changes that you want to bring in production or make it live. For example, you have a Postgres, a blue deployment with Postgres running 14. You want to upgrade to 15, but you don't want to do an in-place upgrade, which it can take longer. So we have a green deployment running Postgres 15. Our implementation is different from the AWS approach, that they made it available for MySQL and MariaDB RDS earlier this year, if I'm not mistaken, or late last year, but they haven't for the Postgres. I'm chasing them because the concept is similar, but we want to reduce the complexity on our infrastructure and our deployment, because it would be nice to offload that to AWS. Really? For our Postgres? In Q3? Okay, that's nice. Thank you. Okay, that's great. Because I asked outside, but the guy from AWS was my SQL, so that's nice. Cool. So why do we need these blue-green deployments? As I mentioned, Postgres RDS gives you the option to do the in-place upgrades. However, this can take a long time and will definitely impact your application. I mean, blue-green deployments is not a near zero downtime. So the application will also be affected, but in a much short period of time. We also need this to, for example, if application needs to run some tests, some performance tests within production fence, meaning with production workload, with production data, they can access this green deployment. Once the green deployment is ready to be promoted, I mentioned the switchover happens without changes to the application. It's not seamless, but it will take much less time. From dozen of minutes, 20, 30 minutes, it depends, to a controlled switchover can take up to 5 minutes or even less. How it works, on that YAML file we set up, we enable the V2 deployment. It's going to create a new cluster. We set up logical replication between them. And then we do that controlled switchover. We disable connections to the V1, which is the blue-green. We confirm there is no data loss, everything is in sync, and then we promote V2.
How do you actually calculate that with data?
With logical replication. So when we set up logical replication, it will create a logical replication slot. It's going to copy the historical data, and then it will start consuming the whole files from that logical replication slot. Obviously, we need to make sure that the logical replication slot is big enough to keep the whole files.
I'm not sure how it works when you actually set up logical.
You don't have to do a dump.
Okay.
So it does when you set up that logical replication slot, it does that for you. And we use PG Logical here, the extension. So, I mean, this is very simple. The blue-green is the V1. Application connects to the proxy. Proxy routes the connections to the V1 at the time of promotion. We make sure the proxy does not have any connections there. We make sure it's in sync. We kill the replication. We remove the replication slot, and then we switch over. As simple as that. And this is done controlled. So we make sure we have checks to make sure that everything is fine. And then we take commission V1. If we want to upgrade when Postgres 16 comes, we deploy V1 as a green deployment, and then we switch over back. We keep 2 clusters, but we don't keep the 2 clusters all the time live since it costs money. So we only set up a cluster. The other cluster, we set up the green cluster when it's ready. When we are ready for the switchover. So we saw how we define the Terraform modules, how we restructure the IAC repository, and how we define the RDS configuration in the YAML file. Now, how from that we get to an RDS, right? From that we can call a Terraform, etc. So we built, our cloud team built the deployment pipeline on top of GitLab. We are heavily users of GitLab. The GitLab is made out of jobs and stages. The pipelines are the top-level component of CI/CD. And I mentioned the pipelines comprise of jobs, which define what it's going to do, and stages when it's going to do. These jobs are executed by runners and multiple jobs in the same stage. And if they are in the same stage or defined to run in the same stage, they can be run in parallel. If all jobs in a stage succeed, they pass to the next stage. If any of the job fails, you may or may not you define on that stage if it can, if the next stage can run or not. In general, pipelines can be executed fully automatic without require of human intervention, but some cases you want to have a human intervention if you want to make sure that you review the output of a stage or the output of a job before you can actually pass to the other stage. So you can manually interact with a pipeline. For Miro, this is an overview of the stages of our deployment pipeline. The pipeline is similar for any Terraform resource. So it's not, we use this to deploy network resources, any Terraform resource, they use the same pipeline. Once the commit, so, and we only have two places or two steps where it requires human intervention. First one is actually a developer pushes the commit. When the commit is pushed, it will trigger this pipeline. So first, it's going to generate the change log for the entire commit. This means in a PR, you can touch multiple resources from multiple RDS, multiple dynamos, etc. So it's going to generate the entire change log. Then it's going to apply canonical. It's going to check if that follows the canonical style, Hard style. If not, it fails. We have to update our code and then push again, and it's going to run again. Then for the change log, it knows what has changed, and it splits the change log for each AWS account because the runners will have to log in with a specific AWS account. So it triggers child pipelines for each AWS account. Then it generates a change log for each one of those AWS accounts. Let's say in staging, it's going to create 2 RDS. In production, it's going to create 1, let's say, in one PR. Then it spins the job per resource to be changed. And so the resources RDS, cluster, and DynamoDB for staging is going to run in parallel. And the one in production for another service is going to run in parallel. So it spins up the jobs that will first validate the Terraform providers. Then it calls the Terraform compliance, which is a lightweight framework for security and compliance. And then it does a Terraform plan for all the resources that are going to be changed or created. If we are happy with the plan and we are happy with the code, the PR is approved, it's merged, and when it's merged, it's going to trigger another pipeline. The pipeline is exactly the same. It does everything with another step at the end that the pipeline is going to actually, when it's merged, is going to create the resources. So there is a new stage, which is Terraform apply. So it's going to do that for you. So let's say, as an example, I had to update my Lambda function, right? I need to tweak some code. We have this Lambda function deployed across over 20 different environments. I didn't want to run this pipeline each time, right? So what I did was, okay, I pushed a new version. I pushed a new code version. This will trigger the new version of the live module for the Lambda. I just updated in the IAC repository for the 20 teragram files. You just do a find and replace. You update the version of that live module, which will point to the new code. And this does everything. So the apply will create a Lambda everywhere. So it saves us a lot of time. what are the main takeaways from here? We managed to speed up and standardize deployments. In the past, it would take much more time to configure all components, and the resources creation were triggered actually locally and not through a pipeline. So it was harder to know who did what. Maybe some people at the same time would change the same thing. So I mean, obviously with the state file is not possible, but there was no control on who was doing what. Speed up, from, I wouldn't say half an hour, 1 hour of this copy paste, etc., and confirming the service name and applying and setting the service, the RDS name with the naming convention. So it would take a lot of time, half an hour, I would say, and then creating it locally. And then after the RDS is created, we have to go set up the exporter, and then the creation of the users, databases, and it was a lot of time. And now the only thing is the PR, it's reviewed, we merge it, and that's it. So it does everything. This is great because we can actually offload this RDS creation to the service teams. And this will give us now much more time for innovation and R&D. What's next? We have more data stores in our portfolio, and we want to apply the same thing. So every data store we have, we create them via terraform. So it follows exactly the same thing. It doesn't matter if it's Dynamo, etc. You create the terraform modules, which have to support that YAML file, and that's it. It uses the same pipeline, and then within the business logic module, you will apply the specifics for the data store, and obviously the other global modules will call different resources. We want to integrate that with Backstage. So we want to actually abstract the service users from actually the IAC repository. So Backstage can be used as a service catalog. And in Backstage, you can choose, okay, I want this new service with this RDS, with this configuration, or for this existing service, I want to use this RDS. That will trigger. So Backstage is responsible to, we call it Backstage to actually create a PR, and it's gonna, follow that pipeline. We want to adopt the AWS Blue-Green deployment, and thank you for letting me know that they're gonna have this ready for Q3. That's great. We can plan on that. We want to make environment cost efficient. So after all data stores are there as a database, as a service, we want to actually challenge what we have, make sure, understand where we are actually spending more money, where we can save money. So there is a lot to do in the test environments, since what engineers do, they test new features, right? They don't test performance, they test features. So they don't have to have a dedicated RDS for a test environment, right? I mean, they can, it can be multi-tenant. We can actually probably move away from RDS in the staging, in the test environment, adopt Kubernetes. I mean, there is a lot we can do in the test environment. Obviously, for pre-production, it needs to match what we have in production, but for testing features, it should be fine. And then other initiatives. So that's the end of my talk. Thank you for attending. Any questions?